start the recording, I think.
Good afternoon, sir, and welcome participant. This is day 5, session 1. I request Dr. Ramesh to deliver his lecture on Ensemble Streamflow forecasting. After his lecture, I'll give you brief about our today's program, that is valedictory function. Thank you.
Thank you. Okay, let's see, 1 second. 1 second. Okay, I'm there. Let me close that one. All right. Okay, I'll go to entire screen. Allow. Okay. Okay. So you should be able to see the screen, right? Everybody? Right?
Yes, sir. Yes, sir. We are able to see.
Okay. Okay. So today I'm going to talk about ensemble streamflow forecasting. This is kind of an old approach, but it is gaining a lot of attention throughout the world. Many forecasting agencies, especially who are worried about floods, are developing what we call ensemble streamflow forecasting, mainly for operational forecasting purposes. So if you see, every division has a hydrological modeling division, hydrological forecasting division, and so on. They do provide forecasts and so on, but when it comes to operational forecasting, that means something which has impact on flood warnings and flood watches and flood alerts, we call it as more of an operational forecasting. That is day-to-day forecasting, or what we call a lead time of 12 hours or 6 hours or 48 hours or so on. We call it as operational forecasting. So what exactly is an ensemble? And of course, we all know streamflow forecasting. We can do streamflow forecasting using data-driven models so that we can get a quick turnaround. We can use black box models like artificial neural networks, regression models based on 2 conditions upstream or downstream. We can use some kind of physically based models like what Dr. Yadav has shown yesterday to simulate the conditions and calibrate and validate for a particular region and keep it ready. So there are a number of ways you can predict forecast for the next few days. Of course, there are important elements which we have to consider when we are trying to predict forecast into the, give forecast into the future, depending upon the lead time. So the idea is that all models are wrong, but some are useful. This is the famous statistician, if you remember the Box-Jenkins models in statistics, time series modeling, or very famous scientist who has worked on many contributions to time series modeling. So obviously, whenever you are developing a model, you are looking for an abstraction of the world. You are trying to take the whole reality and then compress it in the form of mathematical relationships, mathematical functions, either partial differential equations or simple finite difference equations, and you're trying to simulate the whole system using the processes you understand. So you're basically developing what we call deductive modeling as opposed to inductive modeling. So inductive models are mainly which are driven by our what you call data driven. So these are based on available data, what you can get, and then develop your models according to it. So let me go to my screen here, and I'll just start a smart notebook so that I can explain the ensemble forecasting principle in a very general sense. This can be applied to time series forecasting. It can be applied to any other type of forecasting we might do. Okay, so the idea is that we have a well-developed model. We assume that we have a well-developed model. So this is our model. And then we definitely have some inputs. We definitely have some inputs. And we also have what we call the initial conditions, or we want to say it as boundary conditions or whatever you want to call. And then you have the same thing going on the other side. You have outputs. I'm sorry, something. I'm not able to write it very well, but those are outputs. And then you have the model structure and parameters, which need to be obtained by some kind of optimization technique or trial and error. So these are some of the I'd say more than one parameters or parameters. So what happens is that irrespective of all good intentions, we will have problems with input uncertainty. We have problems with initial condition uncertainty. We don't know exactly the initial conditions because we may not have enough number of gauges to help us to provide that initial condition. For example, if you're looking at soil moisture in a watershed, obviously that's a more complicated parameter to be estimated or measured. So if you don't have a good dense network of stations or sensors to help you estimate the soil moisture, you might have an issue with the initial conditions. So there is an initial condition uncertainty, there's an input uncertainty, then we come to the model, then the structural uncertainty. So what exactly we mean by structural uncertainty? The structural uncertainty is something where we are not sure whether we are trying to model the process what we are looking at, and the model is using the right type of equations or right type of expressions to relate to that process. So for example, if you are running a model for an arid region or some other region, so you want to make sure that the structure of the model takes care of some processes, and if the model is able to represent the reality very well from those processes within the model clearly. So that's the structure of the model. Now, that structure can pose some uncertainty in the sense that if that structure is not correct for the conditions what we are applying, so there is a possibility that you may get a different result. So, but the structural uncertainty is most of the time resolved because we know that what type of model we are applying. We know what are the capabilities of the model. We know whether the model can process a particular input or parameters, or a model can represent the processes which are happening within a watershed or within any domain clearly without any problem. So the next uncertainty comes from the parameter uncertainty. Parameter uncertainty is something which we have to deal with it all the time. So we know some parameters very well. Sometimes we don't know the parameters very well. So what exactly we do with those parameters? So anyone has any idea from our students group? What do we do with the parameters of a model? How do we address the uncertainty in the parameters? So if you are given a model and then you have to come up with the parameter values, what would be the first step? What would you do to get your model parameters or estimates for your model parameter values? So each parameter, for example, hydraulic conductivity, Manning's roughness coefficient, or something like that. How do you get those values? How do you make sure that those values are relatable to the field? Those values are reasonable. How do you make sure that? Anyone can respond if you are working in the modeling area.
Sir, from the ground sample we can take and we can conduct some tests. Based on that, we can get those type of values. Or some departments are there of government where these standard values are there for that particular region. From there we can get access.
So basically, the first one is the field measurements. If somebody has done field measurements, right? And
Yes, sir.
the second one is from the existing reports or literature. You can try that.
Yes, sir.
Or
Yes.
you could do your own assessment of the field conditions. You can go ahead and try to use some values. And then the published literature, something which was already published as in the form of papers, or for that area, maybe you can pick up some parameter values. Now, the problem is that even if you take those parameters to be correct at the face value, you still have a problem in calibrating your model. So therefore, we will have the issue of equifinality, that's very well discussed in the sensitivity analysis or uncertainty assessment of hydrologic models. What happens is that for a given initial condition, you might get different outputs. Okay, or for a given initial condition, you can get the same output, but the parameter set will be completely different. So that means your optimization is doing some magic in trying to get the best parameters to fit the inputs and outputs. So therefore, whenever you are choosing parameters, you cannot choose arbitrary parameters and try to calibrate the model so that the results what you get are very well matching with respect to your hydrographs or whatever you are trying to evaluate as outputs. So therefore, you need to have some certainty in your parameters. You need to make sure that your parameters are correct physically, and they are based on the domain knowledge, they are based on some literature, they are based on acceptable values, they are based on some physics, they are based on physically acceptable values. So once you decide that, you still have some uncertainty. Uncertain in the sense, maybe you selected Manning's roughness coefficient, but it varies between within a small range. So therefore, parameters can also pose some kind of uncertainty. So all these uncertainties in a model like this is a deductive model. Why it is called a deductive model? Because it uses the concepts of the system, it understands the system, and then it follows all the dimensional homogeneity rules and everything, and then it comes up with a model. So therefore, it's a deductive model. An inductive model is something which is purely based on data-driven approaches. For example, you want to predict for flooding downstream, you take you take the stage value upstream, you take some rainfall amounts, you take some base flow or other parameters, and then you try to link it to the flow at the next observation point. So that can be a deductive modeling. In deductive modeling, you're not understanding the system, you're trying to put those causal variables which might be responsible for your output, and you're just trying to fit a model using the technology, either artificial neural networks, multiple linear regression or non-linear regression, or you could use model tree approaches or any type of approaches that can help us to relate inputs and outputs, and then we are developing what we call sometimes black box models. So those are inductive models. So in inductive models also, obviously, there is data uncertainty, that is input uncertainty. If your upstream conditions are not measured correctly, or if there is some problem with the instrument, or if you're not sure about the estimation you have done for that particular stage, you'll always end up in some kind of a wrong output. You might end up with negative values of your streamflow or negative values of your stages. So therefore, there is some uncertainty even with the inputs you are providing to what we call the inductive models. So this structure where we are using this concept of understanding the system and so on is what we call the deductive model. Okay, so deductive models are expensive to build. For example, if you are building a Mike-Shee model or some other model, then you will definitely have a lot of issues. Now, where does the ensemble forecasting fits? The ensemble forecasting is a concept where if you vary your initial conditions, or if you vary or perturb your initial parameters, you'll end up with a completely different forecast. So that is what we call the ensemble. So for example, you have a model, and just I'm modifying the initial conditions. I call it as IC, and then I get the output. So my first ensemble is something like this. Then I change this one, then I get another ensemble. Then I get another ensemble. Then I get another ensemble. So you might argue, oh, is it not something similar to sensitivity analysis? No, because sensitivity analysis is looking at how sensitive the parameters are to the output of the system. Whereas ensemble modeling or ensemble-based modeling is not about sensitivity. It's about trying to generate different states of the system or possible state of the system by ascertaining the uncertainty in your inputs or uncertainty in your initial conditions. So that means you can have 1,000 hydrographs for the next day, and each one giving you different peak discharge. So if you are a manager of a particular water agency or manager of a reservoir or a dam operator, then you look at this and then you see if most of the ensembles are falling here, you can actually calculate the probability of that because you know the number of ensembles compared to the total ensembles. You can actually say what is the probability of this value occurring, an average value of that. What is the probability of this value occurring? So if you have less ensembles there, you might have a low probability of that, and you might have a high probability of that value occurring. So that means the models with all the uncertainties most of the time resulting in that darker region, indicating that it's a very high probability that the discharge will be in that particular zone. So that's very important. So what we are doing is we are generating an ensemble of values and trying to make some kind of uncertainty assessment in our outputs, what we are using for our forecast warnings, our forecast alerts, and so on. So that's what is the whole concept of ensemble-based modeling. Okay, so any questions before I move on? Any clarifications on this?
No question is in the chat box, sir.
Okay, no problem. Thank you. So, okay, so basically that's what this particular story tells us, that all models are wrong because none of the models can represent the reality perfectly. So, you know, every time, even if you're using a complex Mach-Chi model, you are making some assumptions about the process. You are linearizing some of the nonlinear relationships. You are making some changes into how you represent the reality, because we cannot understand the complete nonlinearity in the system. We don't understand some processes. We don't have actual measurements to understand the process. So therefore, according to Box, all models are wrong, but some are useful. So definitely, as I said, we have data uncertainty and then model uncertainty. So now the question is, can we generate ensembles based on one model, or can we also generate ensembles based on multiple models? That's the question. Have you encountered this anytime? Anybody? Can you generate, I'm asking you the question, can you generate multiple ensembles, that means multiple results, using different models? Have you done this anytime? Or do you have a comment on that? Anyone? No?
Sir, if we use the ANN and if we try for different structures of ANN, so we can get different results.
Yes. So basically, what you are doing is you're using different models of ANN. So that's again you're generating a different ensemble of the ensembles of your forecast. So that will be useful for you, because so that means that is what we call a multi-model ensemble. The other one is a single model based ensemble. So that means you are developing, for example, when we talk about climate change, there are 50 models, and each model is generating a projection into the future. Now, if you have 50 projections, that's why we do a lot of projections, because when we have all these projections, then we can develop what we call an uncertainty band. We can understand what is the possibility into the future. Maybe we can develop probability distribution functions of the data, what we are getting from the projections of the models, and then we can talk about the possibility of a single value happening next year or something like that. So that's how we can develop multi-model ensembles also. So uncertainty, as we know, it's a result of imperfect knowledge. Of course, sometimes we don't have the complete knowledge of the situation or population under consideration. And that can lead to problems with our predictions, inferences, and conclusions. We don't have that strength in our conclusions, or what we call acceptance of our conclusions. Uncertainty is a potential deficiency due to lack of knowledge. We know that. Error is a component of the uncertainty, which is recognizable as a deficiency. And uncertainties and errors can be, you can use probability distributions to characterize them. And there are two types of uncertainties. One is the aleatory, that is the uncertainty attributed to inherent variation, which is understood as variability over time and space. That means you take a parameter or a process, there might be some inherent variability, which is, we think it's, okay, that parameter varies around that particular value. Epistemic is attributed to our lack of knowledge about the system. So sometimes we think that that parameter influences the whole process, but we don't have a lot of knowledge. Maybe we only have a certain amount of knowledge. So as I just said, there will be input data uncertainty, and there can be model structure uncertainty. When I say model and structure uncertainty, I said previously inadequate representation of the known physical processes inside the model, incomplete understanding about the intrinsic hydrological processes, if you're talking in terms of hydrological processes, and sometimes the modeling and assumptions we make when we are developing models, so the scale at which we think that the processes are happening and the scale at which we represent within the model. There's a mismatch between that, or sometimes a heterogeneity. Maybe the soil medium is highly heterogeneous in one particular watershed, but we sometimes say, okay, maybe we cannot model that completely. We try to make it homogeneous in small pockets, and then we try to develop those models. So there are two types of errors when we talk about data, that is systematic errors and random errors. I'm sure you guys are familiar with both of them. So what is the main difference between systematic error and random error? Anyone? Just quickly so that we can move on. Anyone want to answer that?
Sir, systematic errors are due to known principles or known
Okay.
values, and random errors are like we cannot calculate them accurately.
Okay, so basically you are right. Systematic errors are something which repeat often in the same way. For example, if you have a instrument which always underestimates or gives a measurement which is lower than the observed value all the time by a certain amount, that's systematic error, which can be corrected. Random errors are something which are completely out of our control. So therefore, whenever we call it as random errors, they should follow some kind of normal distribution. So that means these errors do not have a specific rhyme or reason why they are happening, or we don't know what process is introducing an error into your measurement. And for example, you have a rain gauge, tipping bucket rain gauge. Probably over the time it has accumulated a dust particle, and then that dust particle sometimes is causing errors in your movement of the tipping bucket and so on. So those are random errors. These cannot be avoided in our data. Then we have parameter uncertainty. When we get the parameters, some of them are indirectly measured parameters. That means we don't measure them. We try to link it to another parameter, like a surrogate parameters, and then we try to use them. Or estimated parameters, as I just said, we can use literature. And knowledge-based parameters based on the site-specific knowledge. We know that generally in this area the permeability is this much, or Manning sand is this much, and so on. So model structure uncertainty, we talked about inadequate representation, incomplete or conflicting understanding about the intrinsic processes, subsurface or subscale parameters and processes, and modeling assumptions, the scale and the degree of heterogeneity. So the questions are, how are the observation data errors identified and quantified? How do we do that? How to evaluate influence of data uncertainty or overall uncertainty? How to assess the value of new observation or additional data, and how it will influence our parameters of the model or constrain the parameter estimates? How data uncertainty issues can be addressed? How to understand the data homogeneity issues and their influence on calibration, and techniques that can be used for estimating missing values that will affect our calibration again if you have missing values. Joint influence of data uncertainty and model parameter uncertainty. And finally, uncertainty is associated with data augmentation techniques used for ungauged basins or uncalibrated models. So for example, we're trying to develop something where there's a very minimum amount of data. So how do we address those uncertainties? So some of the topics Professor Yadav and other presentations have talked about this. So how do we go about when we have data scarce situations? Yesterday's presentation from DHI Kumar also indicated that what are the issues when we are talking about data uncertainty, where we have to assemble data from previous different sources and try to stitch them together so that we can address that problem. So when we talk about forecasting approaches, when we say forecasting, we are trying to forecast for a next day or next week or next month. But it can be any lead time. I mean, it can be any forecast horizon can be any number of days, right? There can be a lead time also. Lead time in the sense that, for example, if you're forecasting for the next Thursday, you are forecasting now. So the lead time is basically from now to next Thursday. So that's your lead time. So you have that process going on. So what are the different types of forecasting approaches we have? One is the ensemble Streamflow forecasting, which is gaining a lot of attention and a lot of agencies are using throughout the world. Then we have Bayesian forecasting approach, as the approach automatically tells you that we are using prior information, because that's what is Bayesian concept is. Then we have analog forecasting approach. Analogues are historical analogues. That means what we do is, okay, I'm going to forecast for the next 1 week. Right now I have these conditions. So what I do is I go into my historical information, historical database, and then find out when was the last time I saw the similar conditions of humidity, rainfall, temperature, soil moisture, and other factors, and then go to that point and use the information about what has happened in the history and then say that might happen in the history. So it's basically based on your wisdom, and that wisdom is obtained from the historical data. Then we have what we call adaptive forecasting. That means you forecast and you wait for the system to be updated. So for example, you're doing a forecast for your Streamflow, and then you see that things have changed in the last 1 hour. So you use that information to do the update the system and then reforecast again. So that's what all this informations I just said. Prior information in case of Bayesian framework, historical hydroclimatic information, then analog method, and observed hydroclimatic variables, which benefit from these techniques that use persistent to forecast in adaptive forecasting approach. So basically, all this will use the information that is available to make the forecast. But if you look at ESF, that is Ensemble Streamflow forecasting, that is considered more robust to operationally quantify and manage forecast uncertainty. So obviously, for a reservoir operator, for somebody who is taking care of a hydraulic structure or a hydrologic structure, they are more interested in knowing the uncertainty than actual value, because actual value may or may not happen in future. So Bayesian, I just talked about that. In general, operation framework for probability forecasting by a deterministic hydrological model or arbitrarily complex. So what we do is we try to remember what has happened in the past, and a couple of researchers have worked extensively on this one. However, it didn't pick up a lot of steam, even though it's a very conceptually very ideal superior model. But so the idea is to see how prior information can affect your future probabilities of occurrences of events. Then the analog forecasting approaches, they are called weather matching techniques. So that means you take the current weather, what you have seen, and then try to match it to one of the weather conditions which might have happened in the past, and try to see that conditions can be useful for predicting something into future. So for example, if something happens, an incident happens, so you go back to history and say that, okay, we know that this similar type of incident happened at that time, and we know what happened after that. So something like that. So it's basically, now when we are talking about COVID-19, how we are doing social distancing and all those things. There was a Spanish flu in 1910. So we can go back and try to see how the social distancing worked at that time, how the confinement of people, quarantine, and all those things worked at that time. So it's called the Analogues Approach. They are used for forecasting hydrometeorological variables. And then once we forecast the hydrometeorological variables, which are important for us, we can put it in a simulation model to obtain streamflow values for our reservoir operations. I'm just giving you an example. Adaptive streamflow forecasting relies on generation of a deterministic forecast for the next a few days, and you should distinguish between the forecast horizon and the lead time. So forecast horizon is the forecast you are trying to give for a specific period, and lead time is a little bit extra time which you can use it so that you can help for warnings and alerts and watches. As the time progresses, you get more information about the system, you update the system, and you keep on updating the system. And when the system gets updated, you reforecast. Again, you know the system, update the system, reforecast, and so on. So you're adaptively changing your forecast because you are getting more and more information. Like if you're driving from your home to your school, and all of a sudden you see some traffic accident or some problem, and then you try to change your route and then go to another route. And then when you go there, again, there's some problem, again, you make the modification. So it's like adaptively you are changing your forecasting. Okay. So some of the examples, we have a published paper on how we can use it for improvement of reservoir operations, especially if you're trying to estimate hydropower production in the next few intervals, provided the forecast horizon is fixed and so on. So one thing happens is that your forecast horizon will reduce because you're moving towards the end, and then you're updating the system. So as you update the system, in general, the forecasting accuracy will improve. So a good definition of ensemble hydrologic forecasting or ensemble forecasting, we can say streamflow forecasting if you're replacing hydrologic forecasting by streamflow. You call it as ensemble streamflow. A process where a continuous hydrologic model is successively executed several times for the same forecast period by use of varied data input scenarios. That's what is. So why ensemble forecasts? Different model forecasts are provided for a given site and time. How much does model agree with other if you are using multiple models? Agreement can be possible among some models at a specific location. Agreement may not be possible among all the models at another location. So all model forecasts are considered valid as they come from well-established, calibrated, and validated models. So that means if you're using multiple models and you get different results, you still take them on the face value. You say that those are correct because they're all calibrated and validated models. So multiple models can generate ensemble of forecasts. Multiple variations of results from the same model can generate an ensemble of a forecast. Models can use different initial conditions. Okay, physical processes are considered differently in different models. Model structures are different. Model parameters may or may not be best based on the calibration methods, because calibration depends on the objective functions used, the type of solvers used in your optimization. So there are a lot of issues which can affect your calibration process itself. So why use it? Why use ensembles? Model forecasts are uncertain. So ensembles present the best scientific use of the understanding of the watershed processes. So that way, we are saying that we understand the process, but we want to provide the best use of our understanding in a more scientific way. Probabilistic forecasts are better for use, especially for public, than one deterministic forecast. For example, if you say tomorrow there will be a 90% chance of rain, that is a much useful statement than saying that tomorrow there will be 6 inches of rain or 2 inches of rain or this much amount of rain, because that is a vague deterministic forecast and there's no possibility, nobody can confirm that's going to happen. We cannot predict reality in future forever. So we should know some terminology in ensemble streamflow forecasting. For example, ensemble forecasting in general, it's not streamflow necessarily. Spaghetti plot or ensemble perturbation, where you change the initial conditions. Ensemble member, so that is one of the forecast trajectories generated by your model or model run. Controlled forecast, that is the ensemble member or members tuned, from unperturbed initial conditions. Okay, and perturbation forecast started from a perturbed initial conditions. And again, as I said, we don't call them as ensemble streamflow forecasting models. Sometimes they are called as EPS, that is ensemble prediction systems. Okay, so that's the whole jargon or terminology associated with that. So how to create EPS or ensemble prediction systems? Put up the initial conditions in one model, and sometimes there'll be a lot of computational burden. Different models use different processes. You can change the boundary conditions. And what are the main advantages? The main advantages of ensemble-based probability forecasts are when compared to single forecasts. That's the main advantage. That probability forecasts designed to estimate the probability in its forecast are potentially more valuable than single forecasts. They can predict not only the most likely outcome, but also the probability of occurrence of extreme and rare events. That's another advantage. Probabilistic forecasts issued on consecutive days are usually more consistent than corresponding single value forecasts. So if you see, there has been an explosion of ensemble forecasting systems. If you see the last 6 years, new variants of EPS-based forecasting systems have been developed, evaluated, and have transitioned into beneficial pre-operational and operational systems in different parts of the world. So that means not only in theory they were developed, they were also developed in a pre-operational stage, and then also in the operational stage in many parts of the world. So here's in a spaghetti of your spaghetti plot of one of the variables, and this is an example I have picked up from the National Oceanic and Atmospheric Sciences, and you see the forecast. So these are different colors indicate the contours of a particular parameter, and that is not what you would call, it won't give you one curve. There are multiple curves, so they look like spaghetti, which are on top of each other, like a noodles kind of. Okay, so the complete forecast of the probability distribution is not available. It just gives you how these, if all the models or if all the initial conditions by the model are reproducing the similar type of forecast, you will not see so much variability in your spaghetti plots, so all the noodles will stick together. That's how it is. You can also get what we call ensemble mean. That means you can get a mean of all those values at a location and you can plot them, or you can get what we call ensemble spread. You can also get the uncertainty based on the standard deviation also. And we can also talk about probability of extreme events based on the number of ensembles we have. We can also ask about probability of exceeding a specific threshold. If you have something like, for example, I'm interested in rainfall forecast at a particular location, and I say, what is the probability of exceeding a specific threshold of 200 millimeters or 150 millimeters? I can do that. And basically, that's how it is calculated, is the number of ensemble members that exceed the threshold divided by the total number of ensemble members. And sometimes you can also look at dominant type. For example, if you're interested in whether a specific forecast will result in snow or sleet or freezing rain or some other rain, that can be predicted based on what we call a significant impact event. So that is also we can say. For example, if there is a snowstorm coming in northern United States, so we can look at the ensembles of predictions whether there is a snowstorm event will happen or not, and then we can put a threshold for that type of event and then say there will be this much probability that a snowstorm event will happen. Okay, so just to give you an overview, we have different models. We have physics-based models, we have empirical and statistical-based models, and then we have data-driven models. Most of these models are talked about deterministic or stochastic models. And we talked about uncertainty and model errors, and there can be errors because we don't have the complete knowledge of the system. Maybe rare events are not always picked up in the historical record, so that means the model is not learning those rare events. Complex systems are often simplified, scale issues, use of empirical relationship, and sometimes the judgment, experience, and training of those modelers, how they are developing that. So a deterministic model just produces one single output, right? We just take the input data set, put it in the model, and then you get it. A stochastic model, on the other hand, is what we call the probabilistic model. So where we put the random variable of input data to account for the uncertainty, and then we can get multiple outputs. Then we talked about scenario-based deterministic model. That means we change the scenario and we get multiple outputs. It's the same model, it's the same deterministic model, and then we are trying to get different results because we changed the initial conditions or any type of changes from the historical record. So again, when you're looking at forecasting, we look at flood frequency analysis, flood analysis, statistical analysis, trend analysis, and we know that time series analysis or idea is required for forecasting, and then you can have different combination of events, both deterministic and statistic. So here's an example of a time series hydrograph. And time series is what we call a realization. A set of realizations is called an ensemble of members. For example, a set of hydrographs or set of historical precipitation records and so on. So typically what we do when we do a flood frequency analysis, we basically take the historical data, make sure it's non-stationary or stationary, depending upon what our requirements are, and then look at the return period and then try to estimate the flow. It's not a forecasting tool. It generally gives you an idea about what might happen in next 100 years. And we do also flow duration curve. Again, it's not a forecasting tool. Statistical data evaluation, we just calculate all the statistics, but that's not, again, a forecasting model. Trend analysis is not a forecasting model. So a scenario-based approach uses continuous hydrologic model. So what is a continuous hydrologic model? Where the system is updated at regular intervals based on the data which was available or based on data which was estimated or calculated based on the model run in the previous time interval. So you basically continuously simulate the system as opposed to one single event. So you have a lot of flexibility. You can incorporate meteorological forecasts, historical or climate information. You can also include reservoir regulation. It's not a stochastic model, but it only captures what we call the model forcing uncertainty, what we are causing. So multiple scenarios with historical meteorological forecast weather climate data. You can see that you are starting at this location and you can have possible scenarios for your hydrographs. So here is I just indicated some time back, you have a high chance of this level flow or higher, and then medium chance of this and very low chance because the number of ensembles crossing this level is very small. You can see the difference between a deterministic single value forecast as opposed to the ensemble forecast. And we can actually take into account the probabilities, and we can color code them so that it's easy for us to understand the exceedance probabilities. You can also plot like this, same thing. And we talked about all the issues which can introduce problems in your ESP input. It can be the data sources. For example, data comes from radar or rain gauges, streamflow gauges, satellite imagery, reservoir operations, snow observations, and so on. All these things will affect because these are the data sources. And then the model forcing, what we put in the model, that also is going to affect. We talked about the simulation. We can take the historical data and we can simulate them, and so that we can ask the model to understand whether the wet conditions or dry conditions are not. And we can also do conditional simulation based on a specific set of conditions. This is basically the establishing the initial value of your simulation. So the whole idea of ensemble streamflow forecasting is that it's basically we take the three components: the calibration, the forecaster interaction, that means the modeler's experience. We have a deterministic product, and then we start with the ensemble of meteorological data. We process through a streamflow simulation for each ensemble member, and then we get the results from that. And then if you see the analysis window, that analysis window is your time horizon. Okay, that's where our forecast horizon. And we can develop a suite of ESP. So the main components which will affect our streamflow forecasting: ensemble forecasting, that is your soil moisture conditions, land atmospheric connections, long-term temperature, precipitation, and so on. And anytime you are doing a forecast that needs to be verified, I mean, you can call it as validation. Typically, we call it as validation and calibration. Now, validation and calibration are different from verification because when you calibrate a model, you are trying to establish the best set of parameters. But when you validate the model, what you're doing is you're actually using the information what you have from your unused data set, and you're validating the model. So calibration validation happens in not an operational mode. It happens at your desk, in your lab, or when you're working on your research. But verification happens when you make a forecast in an operational mode. When I do a forecast for tomorrow, and then I have given the forecast, and that forecast will be preserved, and then day after we evaluate that forecast and we verify how well we have done. So that's very important, because if we don't do that, we don't understand what is going on. Okay, so there's a whole field of forecast verification. If anybody is interested in looking into that, I have used many of the indices which are available in forecast verification techniques. We talked about that, the skill scores, the probability of detection, and it all depends on whether you're talking about a dichotomous variable like a rain or no rain conditions, or continuous variable. So the forecast verifications are different. There are error measures, there are performance measures, then there are skill scores, then there are contingency measures, and then finally there are measures which can help you to evaluate whether you are doing correctly in space, or whether you are having issues with the persistence, whether you are having issues with your what you call lags in your predictions. For example, you're supposed to predict 200 in tomorrow, but you are predicting 200 on day after. So that means your forecasts are always lagging by a particular, not lagging, but they are superseding by 1 day, or lagging by 1 day. So that lag also needs to be evaluated both temporally and spatially. So you need to look into what we call forecast verification. So please understand that forecast verification is not same as your validation. For that matter, verification is not same as validation. So what are the ESP products? You can get stage, discharge, you can get runoff volumes, and we can do what we call statistical analysis of the exceedance probabilities when we get the results. We can do conditional discharges. We can also do the flood inundation map likelihood. So for example, this is the ensemble of daily flows. Then we can do some kind of summary probability plot like that. And if you're talking about probabilistic flood mapping, then you are looking at the ensembles of the inundation area, and then you can talk in more probabilistic sense that, okay, the probability of flooding is less than 25% for that, for the yellow part, it's so on, and then greater than 50%. So that is based on our ensemble predictions, and then of course we translate that into a spatial value. So that's the advantage of the predictions. So ensemble streamflow predictions, in summary, they will help us to look at the scenario-based hydrologic models, and historic or forecast hydrological data can be used. You can create an ensemble of streamflow simulations, and the flexible output and verification tools are being developed. So for example, all these operational systems, they are working on verification tools, because that's what gives them confidence in their forecasts. If you're not verifying, then you have a problem. So here's a small example I will quickly go through. So typically, because you're trying to change your data sets, we have to work with some random numbers. So if you know, we do a simple random sampling of your data set, or we can do a Monte Carlo sampling of your data sets, which is same as simple random sampling. And then we also have what we call the Latin hypercube sampling, which you might have remembered from your theory, or you might have already implemented in your research. So random numbers are beautiful. They are like pseudo random numbers because they are not really random numbers. Random numbers generated from a computer are called the pseudo random numbers. So is a nice example of how random numbers can be used. For example, you can generate a key of random numbers. You send a message to somebody, and then you provide the key to somebody, then they will extract the encrypted message by removing the random numbers. They get the actual message. So this is like our dual verification systems, exactly like your what is that? You get a message on your phone confirming OTP, right? OTP, something OTP, I think. Yes. So Monte Carlo simulations are very good because we generate random numbers and help to solve a lot of problems. Random numbers, we think that they are only helpful for creating uncertainty in our data sets, but they can also help us solve. We can use Bootstrap sampling, that means sampling from the same population, and that's what is also called as the resampling method. So an example of Monte Carlo simulation is, for example, if you are trying to estimate the value of pi or area of that circle, for that matter, all you have to do is generate a lot of random numbers and then count the number of points inside the circle, and then the total number of random points. And then if you do the calculations, you can actually calculate the area of a circle very accurately. So that's the one application of Monte Carlo simulation. Here's an example of how you can calculate the value of a pi using Monte Carlo simulation. So basically using the area of that 1/4 circle. It's also useful for calculating definite integrals. For example, if I want to calculate the area under that particular curve, which cannot be analytically solved in calculus, then I can use Monte Carlo simulation for getting the area of that particular dark region. What is Latin hypercube sampling? Latin hypercube sampling ensures that, because if you take a simple random sample, they might, or sometimes a random sample may fall only in one area of your data set, or the one range of the data set. Let's say, for example, your value varies between 1 and 5. If you take 1,000 random values of between 1 and 5, sometimes you will get more in one area, like from between 4 and 5, and less in the other area. So what we do is in Latin hypercube sampling, what we do is we break the entire range of the variable into a fixed set of intervals. That means equally likely possible ranges, and then we draw the samples from each of them. So here's an example between a Monte Carlo sampling from a normal distribution, 10 and 3, and you can see the Latin hypercube sample, which is resulting in more normal random samples compared to the previous one. So this is the inversion method. If you're using a simple random sampling, you go from the probabilities and you get your value. But in LHS, that is Latin hypercube sampling, you divide the whole range of 0 to 1 into equal 10 intervals and then get the values. So that means your representation of the range values is perfect when you do Monte Carlo sampling. So this is random sampling and this is Monte Carlo sampling. So again, the same thing with the Latin hypercube sampling. So that gives you a better idea that sometimes when you randomly sample within a range of values, you might end up having more values on one side. So why that is a problem? Because when you're trying to do an uncertainty assessment of your data, which goes into your models, then you might have a problem in explaining why you are not covering some part of the range of your variables. So therefore, we have to go for Latin hypercube sampling. So here's an example what we try to evaluate the influence of soil moisture storage on peak discharges. Okay, we use the HEC-HMS, the soil moisture accounting model, with Monte Carlo simulation. So basically what we have done is we are not sure about the soil storage capacity. So for example, in Florida, we have high water table. That means if you dig 4 feet, you will start seeing water. So what does that mean? Because ours is typically a wetland, which was restored to urban areas and so on. And we have a lot of recharge happening. We have a lot of rainfall, too many lakes, and all these things, and a sandy type of soil will contribute to what we call high water tables. So whenever you are looking at the water table below the soil, that water table influences the soil storage capacity. So this is what is the problem. And as we go 1 feet below, you have some storage capacity and so on. So this is what we want to know, that how the soil storage capacity will influence the peak discharges. So as the groundwater goes up, you are losing the storage capacity. That's what it is. So what we do, we take the soil storage parameter, we introduce a perturbation scheme like a random or Latin hypercube. We run the HMS, soil moisture accounting model in Monte Carlo simulation. And then from that, we obtain the soil storage values. We put it in the basin parameter file within our HMS, run it multiple times, and then we get the peak discharges. This is our soil moisture accounting model. And one advantage with that is it accounts for the soil storage as we move in a continuous mode. So you might have seen this. This is the soil group classification and land use for that location, a small watershed in Florida. The outlet is here. Unfortunately, these are the rain gauges. For some reason, they are not represented well. These are the evaporation rates and the lat long of that. And we are using the unit hydrograph method for our transformation to get the discharge, that is peak discharges. And then we use Monte Carlo simulation. And we sampled, 100 values. So you can see the difference between a histogram based on random sampling. You can see the variability, sometimes more in some areas. Whereas here, you can see how in each bin, the values are picked up really good so that you have a uniform representation of the sample. Then we evaluated the model performance by looking at correlation coefficient. We're looking at mean absolute errors based on the sensitivity to the soil moisture parameter. So you can see that the correlation is highest with the observed discharges whenever we have one value. So this is possible because we are trying to ascertain the data uncertainty, or at least in this case, the parameter of soil moisture. We don't know exactly, so we are doing that. And the mean absolute error, again, goes down at that particular parameter value. Unfortunately, they don't coincide very well, but at least we know the range in which we are getting the best correlation and the lowest mean square. So these are some of the results based on both LHS and random. And you can easily appreciate the average flow is constant when we are talking about the Latin hypercube sampling, but it varies based on the random sampling. So these are similar examples based on when we get that correlation higher than different values, and then mean absolute error. So we did some sensitivity, and then so the insight from the results are for all the 3 MAP performance criteria, the variability of the number of random sample simulation chosen is higher than the number of LHS sample simulations, which is kind of expected, but it is interesting to see. And also we saw that the mean soil moisture storage did not coincide exactly when we used 2 different performance measures like MAE and correlation coefficient. Simulations based on random sample time series show more variability than simulation based on LHS, which is agreeable. We understand that. And significant increase in the correlation coefficient of variation is noted with the personing of performance criteria. So these are some of the things what we have done. And due to lack of information and the data, how the soil moisture varies, we have assumed uniform distribution. But if there's any other investigation, we could have used some other sampling to do the Monte Carlo sampling. Okay, so that's the and the idea for this work is to say that the sampling schemes will also have impact on the outputs we get, and of course the flow volumes, everything. So therefore, we have to be careful. So just to conclude that the ensemble-based systems are becoming more popular now, and you can see that there are several operational systems now. The European Flood Alert System, the Finnish Hydrological Society, Swedish one, US NOAA is using now, Meteo France is using. So there are so many operational ensemble streamflow forecasting methods are being actually implemented in use in many parts of the world to give you those predictions. So as I said, many of them are applied, and over 15 operational and pre-operational systems called referred to as hydrological ensemble prediction systems are around the world. These approaches have led to improved multi-objective driven reservoir operations. This is one of the take-home messages, that because of this ensemble Streamflow forecasting measures, the reservoirs operators have a little more control on how they can handle the flood which is coming in, because now they don't have a single deterministic forecast, they have what we call probabilities associated with that. Some of these ensemble Streamflow forecasting methods are used for long-term Streamflow forecasting, considering the climate variability. That means, let's say, for example, La Nina, El Nino situation. So if you know the seasonal, if you want to do a seasonal forecast, that also in an ensemble way, then you might want to include the possibility of the climate variability, because climate variability influences your meteorological variables. So EPS system-based forecasting can improve the operation of considering the uncertainty in the Streamflow forecast horizon, and the value of information gained from forecast. They were considered very critical in many studies. The other unfortunate thing is ESFs in many parts of the world, they have experimented, but they don't report any failures. So that's where the forecast verification becomes very important. So we also need more pilot studies that form the basis for the development of operational systems, and efforts are needed to encourage forecasting agencies to design more EPS systems to forecast, or communication to non-experts. Operational flood forecasters were more often skeptical about the ability of the forecast recipients to understand and use them appropriately. What does that mean? That means basically the probability-based forecasts are given, but the operators who are using them are not sure about what are these things, or sometimes the modelers who are generating these probability-based forecasts, they think that operators are not understanding what they are trying to do. QPF, that is quantitative precipitation forecast, combined with the climate information, can translate improvements in forecast skill. So now we have a nice quantitative precipitation forecast, what might happen in future, and that can help us in improving the skill of our models. And we also need to see that we invest resources. Now, data assimilation capabilities, when we say data assimilation, data which is available from different sources at different temporal intervals need to be assimilated so that we get one homogeneous data set. Okay, that's the whole idea of data assimilation. So ESF approaches cannot eliminate the uncertainty associated with future forecasts, but reduce the uncertainty. Okay, so nobody can eliminate uncertainty. We can reduce. They can be useful to communicate risks associated with forecast events. So, as I said, we can talk about probabilities as opposed to one deterministic single value. So, floods and droughts are rare events. We know that. Availability of archive of historical event-based data, including meteorological conditions, is critical, because if you are calibrating and validating ESF approaches, you want to have that historical data which has resulted in a specific flood or drought. Okay, and we need more databases so that we can keep this data, the long-term historical data, so that we can develop better ensemble Streamflow forecasting methods. So that is the whole idea about ensemble Streamflow forecasting. If you have any questions, I will be happy to answer at this point.
Yes, sir. There are a few questions. Let me start with the first one. Sir, what can be the possible methods to penalize the wide ensemble ranges? Sometimes it results in more number of false alarms due to this.
So when you are running your forecasting model and you are getting a, that's why they say, right, you need to first make sure that your model is well calibrated and validated before you start doing ensemble Streamflow forecasting. So that is first. So what you get from your ensemble Streamflow forecasting, you have to accept in a face value, because your model is already calibrated and validated very well. So unless the model is, that's why the forecast verification comes. If your forecast verification is suggesting something completely odd, that your model is not able to predict something, or it is out of the out of the ordinary, so it's saying like heavy stream flow based floods are happening when there's nothing happening, then you have to go back and see what is the problem with your model structure or your data uncertainty. So that's why I'm saying we need to preserve the historical data so that we can see and calibrate our models very well.
Sir, excuse me, sir. This is Rashmi. Sir,
Yeah.
I wanted to ask that sometimes in the data itself, the data which we are meteorological forecast which we have downloaded from some website like TIGI and ECMWF, how can we penalize that wide ensemble range, sir? Means there is a very wide data sets, means wide range of data set. Then what can we do for that?
So you are saying, for example, the forecast you are getting from a particular site
Yes.
for a particular variable, for example, precipitation, has a wide range. That's what
Yes.
you are saying.
Yes, sir.
So that is the forecasting, what you call the input estimation uncertainty, that you cannot do anything. We cannot penalize the input uncertainty which is coming from a particular source. This is same as the data uncertainty. You are getting an input, you
Yes.
have a lot of uncertainty in that. When you say penalize, what are you trying to say? That means you don't want to take some of the values in your model, or what do you mean by penalizing?
There are very high precipitation which are being given in those forecasts. So how can I, yes, sir. So what method
So
I can use?
we cannot eliminate them. We still simulate your model based on all the available forecast of
Yes.
precipitation, because that forms your input.
Yes.
Now, if the ensemble results, what you get out of your model, indicate that the probability of having that event happening is so low, then we can remove that as a possible forecast later on. So, for example, if it is a very high precipitation forecast, when you
Yes.
pass it through your model, it'll give you a very high flood value. Now, when you run thousands of ensembles like that, maybe the model telling you for 1,000 value is only a couple of times, but the rest of them are falling below some value. So that means those two values can be easily neglected, because the probability of having a high flood is so low that we can neglect them. So that's why the probabilities are associated with your ensemble members. And the members which come out of your hydrologic model, you have to do some probabilistic assessment. You need to fit a distribution, or you need to see the spread of that values. That's what we have to do. But we cannot penalize or eliminate one particular forecast given by a particular agency. We cannot remove that, because that is a part of the data uncertainty. Let it go through the model.
Yes.
When it comes out of the model, then you can say that I'm not going to use this forecast, because this forecast is way out of our range, and this is one of those outliers or anomalies, and I will remove them. That's fine. But you cannot remove what is a valid forecast from an agency. If an agency says it's going to be 200 millimeters tomorrow, we have to take it as a face value and run it through our model. That's what we have to do.
Okay, sir. Thank you.
Yeah.
Rashmi, you posted some question in chat box also. So may I read to those questions also, or this is enough?
Let me read it. Let me read it in the order. Okay.
Yes.
So they have it. We can have. Ayushi says, can we have? We can have different outputs with the different models with the same data. Yeah, it's a possibility. Yes, it is. It is definitely possible, but at the same time, we can have something different. Somebody's agreeing. I think little output variation happened in GCM output. Sometimes it happens, but sometimes you can have different. GCM models can produce completely different results, completely different trends actually. One is saying increasing trend, the other one is no trend. We talked about penalizing wide ensemble ranges, especially in data. We cannot penalize what is coming in as an input to your models, but when the results come out, you can eliminate some of them for being very less likely. and you can remove them. What is the difference between forecast horizon and lead time? Forecast horizon is, as I said, for example, if I'm standing now, today is Friday, and I'm forecasting from next Thursday to next Thursday, Friday, Saturday, Sunday, 4 days. Those 4 days are my forecast horizon. The lead time is from now to Thursday. That is your lead time. Okay, so lead time is the time you keep to give an advanced forecast from next Thursday to next Friday, Saturday, Sunday. That's so next Thursday, Friday, Saturday, Sunday are your day of horizon. The 4 days is equal to forecast horizon, but the lead time is this extra time you are gaining to make the forecast. I hope I made that clear. While using parametric post-processing methods, can you suggest that what data length, how many years of monsoon months in case of precipitation will be sufficient? Again, it is site specific. It is always in statistical methods. If you are trying to look for post-processing of your parameters, the more the length is good. Whatever you have, use it. You cannot say that there's no sufficiency condition. The more knowledge you have about the parameters, the more data you use in your system, you have more confidence in your parameter values or estimation or processing or any process for that matter. How the forecasts are perturbed, how reliable is this forecast to be used for modeling purposes? Unfortunately, we don't perturb the forecasts. We only perturb the inputs. We perturb the initial conditions for the model. We might perturb a little bit about the boundary conditions. We might perturb the internal parameters. So all the perturbation schemes are before you get the forecast. So we don't perturbate the forecast. We forecast the input domain, the model parameter domain. That's what we do. Whatever we get, that is our final perturbed ensemble of forecasts, and we have to deal with it once we get those ensemble. There are many approaches to generate ensemble forecasts, including data-driven techniques. But data-driven techniques sometimes overpredict. In this case, how reliable is this use data-driven predicts for generating ensemble streamflow forecasts? Okay, so now we cannot say what you call. We cannot come up with a statement, a blanket statement that data-driven methods always overpredict. Okay, they might underpredict also. And data-driven models are much easier to apply. For example, if you're doing a forecast of stage next station, which is 10 kilometers from here, and you have a stage here. Okay, so you can consider a forecast horizon. You can consider the lead time and all those things, and you can predict if the data-driven model is well developed, well calibrated, well validated, the forecast it will provide will be within a reasonable range. That means even if you perturb the input parameters, for example, the stage at one location, you can perturb a little bit so that you get completely different values. But to say that most of the time they overpredict is a little bit uneasy statement, right? So sometimes you said they will overpredict, but that is the limitation of a model. When you are talking about even of the physically based models also sometimes overpredict. So we cannot do anything about that. That's why before you develop your ensemble streamflow forecasts or any type of ensemble of future forecast systems, you need to make sure your model is well calibrated and well validated. And after you do the ensemble forecast, you need to also verify how well you are doing. If you are doing badly, you have to go back to the table and then modify the structure. For point source forecasting is easier, but how to approach same with satellite data, precipitation, and temperature? Moreover, carbon emissions are a cause of major climatic change. How do you take into account? It depends on what is your time horizon. Okay, so typically operational ensemble streamflow forecastings are for real-time applications or short-term applications, not for long-term. So therefore, climate change may not come into effect unless you are doing some seasonal forecasting. Seasonal forecasting is also mostly driven by climate variability. For example, right now, standing now, I can do an ensemble of forecast for the summer monsoon in India. And when I'm doing an ensemble of summer forecasts for monsoon in India, I have to consider the conditions of La Nina, how La Nina and IOD will affect the seasonal forecast. So those things should be embedded into my model or to be considered into my model. But climate change is much longer. So whenever we are talking forecast systems, we are not talking about short-term forecasting systems when we are talking the ESP methodology. But however, if you are talking about GCMs, yes, they are projecting into the future. They are considering the climate change aspects. They are considering land use. They are considering everything, carbon emission and all those things. That's why if you are using 50 GCMs, 50 GCMs are providing 50 ensembles of results for you. So that's why there you can take all those 50 ensembles and do more of a probabilistic assessment of your results. How long your forecast horizon can be, it depends on what is your application. For example, if you are trying to do a forecast for your agricultural area, maybe 15 days. If you are looking at water supply, it can be months. So it depends on your the problem, what you are trying to forecast and what is objective of your forecast, how your forecast will be used. That's important. Do ensemble models used for operation purposes have some adaptive nature as well? Yes, of course. Every ensemble model will have a kind of condition, as I said, verification and status update, right? It's like driving your car. You're always doing adaptive forecasting when you're developing real-time forecasting, because the atmosphere is very dynamic. Hydrometeorological inputs are very dynamic. They change often. So what do is you do a forecast, you wait for that event to pass, and once the event is passed, you update the system, then you do again ensemble forecasting. Okay, Yushi says, either black box models or physical models are reliable for forecast. What approach is developed in developing countries? Okay, so again, this is a problem where you are talking about the computational resources, the density of your network, the understanding of your watershed, the understanding of the physical processes of the watershed. So for example, for operational forecasts, if you can run your Mike Shee model or Mike 21 model for your flood forecasting, you can do it, but you need to have confidence in all your parameters you are putting into your Mike Shee model. So it's like garbage in is equal to garbage out. So if you put all those wrong parameters, you have sparse density of network of measurements, then physically distributed models or these complex models where you are discretizing the domain, the topography, the parameter field, and everything, they may not result in good forecasts. Whereas a simple data-driven forecasting based on regression may work out very well in those situations, because you're taking the complexity of your watershed, and you are not modeling, you're not sampling very well to understand the physics of the process, and that's where you cannot run a physically based model. So if you can have a strong physically based distributed model, if you have calibrated it very well, you have a strong density network of stations, and you are sure about validation, and if that model can be run fast, maybe 2-3 hours, yes, you can apply for future ensemble forecasting. But if all these conditions don't apply, then a simple data-driven model sometimes may perform very well for forecasting flood stages into future. For example, water level forecasting in artificial neural networks. There are so many papers where they were able to achieve very good stage forecasting. Okay, so in statistical, let's see, post-processing of meteorological forecasts, which should be preferred, parametric or non-parametric? Well, once the data comes out, the only question you have to ask is, if you want to process it, you have to check the distributional assumptions of your parametric tests. Parametric tests most of the time require normality. If the data which comes out of your forecasting ensemble does not follow normality assumptions, then obviously you cannot use parametric tests. Parametric tests are much easier to use. Non-parametric methods are much easier to use because those are distribution-free methods. There is no pre-specified required assumptions for non-parametric methods. So you can check first the data for conformity to normality, and if they doesn't pass that test, go for non-parametric test. Okay, good. Any other questions? Looks like we are good with the questions. I hope I answered all the questions.
Sir, if you have time, then can take up quickly one question, or otherwise I will ask him to email you. It's already 5 o'clock.
It's already 5 o'clock. It's 5 already? Okay. Oh my goodness. Okay. So then I have to. Okay. Please go ahead. I have to join the other. Yeah.
Yes, sir. Sure. I'll ask them to mail. Okay. Thank you.
No, you can ask quickly. You have time. 2 more minutes.
For a point source streamflow forecasting is easier, but how to approach same with the satellite data of precipitation and temperature? Moreover, carbon emissions are also cause of major climatic change. How to take that into account?
Okay. Again, I think I answered this question in a way, but the point source forecasting is at one single location is always easy. But the problem is that if you want to do spatial forecasting, in the sense you want to forecast at multiple values what is happening, you have to use like our distributed hydrologic simulation models. So again, the ESP concept is not for long term. So therefore, the climate change signals are not considered in ESP. ESP is only for short term. It's just like 15 days, 1 month, or at the most seasonal. Like as I said, gave you an example of Indian monsoon. So that's the closest we can go. For long-term predictions or long-term forecasts, you have multiple GCM models, and it becomes a multi-model ensemble. So you have 60 models which are telling what will happen in Gujarat in a particular location in future. So you can take all those ensembles, and then you can start working on your assessment, probabilistic assessment or post-processing of those ensembles. We can do that. But ESP as a concept is more dynamic, short-term, and it is close to the time you are looking for. Short-term, very short-term. There are not many ensemble streamflow forecasting methods that are being used in developing countries. Developed countries have already adopted them. It is because they are data hungry, computationally more expensive. You need more data. You need more, what you call computational infrastructure. Then also there should be a dense network of stations which can provide you a little more confidence in your initial conditions. Then only we can be successful. So for developing countries, we can develop some simple models and still provide, for example, yesterday when Professor Yadav was talking about the flash flood in Mount Abu and that area, you can probably by perturbing, if you have the rain gauges in Mount Abu, 1 or 2 rain gauges, and if you have 1 soil sensor in that area, maybe you can develop an ensemble-based streamflow forecasting based on what is going on to happen in the next 5 days and give that probabilities to a reservoir operator. You can still do that. So if you have a well-calibrated, validated model, generating ensembles is very straightforward, because all you have to do is perturb your soil moisture a little bit up and down, and you get an ensemble of stream flows, and you can calculate the probabilities and tell the reservoir operator, hey, there's a probability, 90% probability that your spillway will be active for this particular flood. So you start doing something about it, because 90% is high chance. So if somebody says 90% chance based on your ensembles, then the flood alerts and flood warnings for the downstream communities is also an imperative. That means you have to make that, because they can escape that flood. That's what it is. But you can be safer than sorry than safer, or whatever they call. So maybe if it doesn't happen, that's okay. But still, you have some level of assessment from your models. Okay.
Okay, sir. Okay. So we'll meet again at 6:45 p.m. Okay. as
6:45
India
p.m.
time. Yeah.
Okay, thank you.
Okay, thank you, sir. Thank you so much. Thank you. So participants, please turn off your camera, turn on your camera for attendance of this session. Rashmi, done?
1 minute, sir. I request everyone to switch on their cameras.
There are 1 or 2 participants who have joined using desktop and not having camera.
Yes, sir. Taken, sir. Thank you.
Okay, so we will meet after 15 minutes. At 5:15, we will start our tutorial session. All are requested to keep pen, paper, and calculator with them, so that simultaneously we do calculations and you can get idea that how AHP exactly works. So thank you. We'll be joining at 5:15.
Sir, in this break time, I will be sharing the feedback form. So I request everyone to fill the feedback by going to the website of Gyan website, IIT Kharagpur, and logging into their portal. So they can see the feedback, awaited feedback at the top with the registered course, and they can fill the feedback. I request everyone to do it. Thank you.